This is Precalculus, Chapter 12, Lesson 1 on page 779. All right, so now we're moving to systems of equations, which that really is all that a matrix represents, is a system of equations. We've worked with systems of equations before, like when I had 3x plus 2y is 7, and maybe 4x minus 5y equals 6. That is a system of equations. All right. I have how many equations? In this one. 2 equations. How many variables? 2. 2 variables. So if I were looking at a matrix, it would be a 2 by 2. 2 equations, 2 variables. All right, we can write this as how do we solve these? Substitution or elimination. It's exactly what we're going to do when we get to matrices. All right, so this can be written in one or two ways. And when I'm talking with equations and variables, it's really a 2 by 2. But if I were to write it as a matrix, I would write it as a 2 by 3. So everybody watch. I'm just going to write this as a matrix so that you just understand that all a matrix is, it's a system of equations. That's the matrix for that equation. What did I do? Yes. I took out the x's and the y's. There's no variables. And the equal sign. Yes. If this is in a matrix, this is a 2 by 3. It's rows by columns. So if I have 2 variables, in order to solve a system of equations, I have to have 2 equations. If I have 3 variables, how many equations must I have? 3. 3 variables, 3 equations. All right, so that would be 2x plus 2y plus 3z is 1. And then 2x minus 5y plus 2z equals 5. And then x minus y plus z is 20. I don't know. I just made that up.
As you keep getting bigger and bigger, you have to have the same amount of variables.
Correct.
X, Y, Z.
I have to have the same number of equations as I do variables in order to solve the equations. We in Algebra 2 have solved these types of equations. If I'm looking at equations, I have 3 equations, 3 variables. You have to have a square number in order to solve the equations. So you have to have a 2 by 2, a 3 by 3, a 4. But if I were to write this in matrix form, what would it look like?
3, 2, 3, 1, 2, 5, 2, 2, negative 5.
Negative 5.
2, 5.
Yes.
1, 1, negative 1. Yeah. 1, 20.
Yes. And what would I call this? A what by what?
3 by 4.
3 by 4. Got it? A 3 by 4. Rows by columns. All right. In this first lesson, it's 100% review. We're going to use algebra, substitution and elimination to solve for x, y, or x, y, and z. At what point could I have a system of, let's just say, 2 linear equations and they have no answer in common? When would that be the case?
There's 3 variables?
Well, if I have 2 linear equations and then there is no solution if I use substitution or elimination. Like if I had, okay, I'm just going to make it easy. That's not what I wanted to do. I'm going to write it in a different manner. Okay, this system of equations has no solutions in common. Why? What do you think, Isaac?
Is it
Because
because y equals 2 different things?
y equals what?
2 different things.
What has y doesn't equal one?
Because 1 doesn't equal 5.
No,
Yeah.
that's not the real reason. If I graph these lines, would they ever intersect?
Yeah.
They
Wait,
would
no,
never.
they're-
Because they're parallel. That's why. Same slope, different y-intercept. The lines are parallel. There are no solutions in common. So this would be called, we had one lesson in algebra, inconsistent. The word consistent means at least one solution in common. All right, so let's see what happens when we go to solve this system of equations. I have y equals y equals. I'm going to substitute this for y.
Yeah, you just get
Okay, so I'm going to have 2x plus 5 equals 2x plus 1. When I subtract 2x from both sides, what happens?
We can't
Use 5 equals x equals 6.
5 equals 1 and then it
Does
doesn't
it?
make sense.
Yeah.
That's right. It's a fallacy, right? It will always be inconsistent when you have something equaling something. You might have 0 equals 2, but it's illogical. Your systems of equations will always be inconsistent when you have this illogical statement. So when it's inconsistent, you know the lines are parallel. So inconsistent means
Parallel.
parallel. That means they never intersect. That means consistent. Consistent means they have at least one solution in common. Okay, consistent can also mean every solution in common. So if that were two lines, one on top of the other. It's consistent at every point. Okay? This is when it would be consistent. All right, so let's maybe write this down. Inconsistent. What does inconsistent mean? Means they're parallel and you're going to end up with some illogical statement, right? The lines are parallel. Consistent is one of two things. Either you're going to get x equals a number and y equals a number. That's the point where they're consistent. That's typically what we arrived at when we used substitution and elimination in algebra 2. Do you remember that? Or you're going to end up with 0 equals 0. All right, I'm going to show you this. So I'll show you two equations that are exactly the same. Let's change this one. All right, those are the same exact equations. You know what I did? I just multiplied the first equation by 2 every term. They're the exact same equation. Okay, but let's suppose you can't recognize they're the exact same equation. Let's try to use elimination. So how would you, what would you do to eliminate?
Multiply the top one by -2.
Okay, I'd multiply the top one by -2. So you end up with negative 6x minus 4y is -4. What do we end up with? 0 equals 0. This is how you know that they are the exact same line. They are consistent at every point. Every point. It's going to be important when we get to matrices. It's going to look the exact same. Or you can just have one solution for each of the variables. I believe that is like example 1. All right, look at example 1. We have 2x minus y equals 1. We have 3x plus 2y equals 12.
So you just put into your calculator this lesson, is that what it was?
No. It probably does say plug it in your calculator, but no, we're going to use algebra. What would you do, Isaac?
Make the first equation y equals 2x minus 1.
Okay, you would solve for y.
Yes.
Okay.
But you can just eliminate.
Or you can eliminate. It doesn't matter. I prefer elimination,
See, that's just what first came.
but substitution works. We're going to use substitution. So y equals 2x minus 1, right? Substitute this in for y. So you have 3x plus 2 times 2x minus 1 equals 12. So it's 3x plus 4x minus 2 equals 12. Add the 2. 14 is 7x. What's the value of x? 2. How do I solve for y?
Plug 2 in for x.
Right. So 2 times 2 is minus 1. This is the point where they are consistent. They're consistent at one point. So did you see the 3 different options?
I just like that this is really.
I don't think that that's right.
It is.
3, 2. Wait.
X equals 2, y equals 3.
I think they, because you
Right before the blue line.
You know what?
Just right above the blue line, or the line above solving systems with graphs. Okay, this is review, isn't it?
Yep.
Yes.
How would you do the elimination? I forget.
Okay, let's do elimination. Let me erase this one. Yes, I multiply this first equation, Corey, by,
2.
so you'd have 4x minus 2y equals 2.
And then you can cancel.
So you would have 7x is 14, x is 2. Same way, doesn't matter what you use, right? Okay. So we have 3 options. Those 3 options are on the bottom of page 781. If the lines are parallel, they're inconsistent, there are no solutions in common. Like we just solved, there's one solution there. It's a consistent system. Only at one point. We're solving for that point of intersection. Or when you have 0 equals 0, you have the exact same equation. They're consistent at every point, and there's an infinite number of solutions because every x in one equation, every xy coordinate in one equation is equivalent to the xy coordinate in the second equation. Does that make sense? Should feel like a little review. All right. We're not going to do example 2. We're going to do example 3. All right, so if we have 3x minus y equals 12, and we have 2x plus 3y equals 2, what would you use? Substitution or elimination?
They chose to substitute. I would use elimination.
I would use elimination as well.
This one.
Wait, what am I talking about? Yeah.
Okay, why, Lucas, do you think my initial thought is elimination?
Well, no, I was thinking elimination, but I
Substitution. Okay, Corey, why?
Because there's a one value and you can just multiply it.
And the signs are opposite. It just makes it easier. Even though the book said use substitution, we just use substitution. So now we're going to use elimination. All right, so now we have 9x minus 3y is 36. When we add them, we end up with 11x equals 38. Is this right? X equals 38 elevenths? Yes. Do not write it as a decimal as your textbook does. Now to solve for y, how do we solve for y?
Plug that back in.
To which one do you think?
The first equation.
I'm absolutely going into the first equation because it's just y. So it's 3 times 38 elevenths minus y equals 12. What's 3 times 38?
Then 114.
114 over 11 minus y equals 12. Now what would you do?
Add 14.
Add y, subtract.
Okay, I'd do something different. What?
Oh, you would add one.
Add y, subtract.
When you have an equal sign, you... Wait, somebody said it. Equal sign. Eliminate denominator. Oh my goodness. Multiply every term by 11. Okay, those of you that had me last year, you should remember this. So we have 114 minus 11y. What's 12 times 11?
130
That's 11 times 11. 121 is 11 times 11.
132. Yeah, I said 132.
132.
I said 132.
I know, but is that right?
Well, if you,
121 plus 11.
it's 11 to, yeah.
It's another 11.
Okay,
Yes.
times 12.
Okay.
132.
Subtract 114. What do we have? Negative 11y equals, what do we have? 18?
Yes.
Is it 18? So y is negative 18 elevenths. Okay, so what are these systems of equation? Consistent or inconsistent?
Consistent.
Consistent at how many points?
1.
1. Make sense?
Wait, how do you do it? Oh, yeah.
How do we know this? Someone explain it. How do we know they're only consistent at one point?
Because they intersect.
Okay, but we don't see them graphically, but how do I know by doing this process that they're consistent only at one point? Yes, Isaac.
Because it's not 0 equals 0.
Correct. We didn't end up with 0 equals 0, which would mean they're the same equation. There's only one solution in common. We come up with a unique x and a unique y. Make sense? All right.
Wait, so if 0 equals 0, they are consistent.
If 0 is 0,
Right, we're not going to do example 4 because it's the exact same as what we just did. We're going to do example 5. All right, so turn to example 5. All right, we have 2x minus 3y equals 5. And we have 4x minus 6y equals 1. All right, what would you do? Eliminate. What would you eliminate?
just multiply by 2. Negative 2.
X.
The top.
Yeah.
Okay, the top one by negative 2. So I end up with negative 4x plus
6y.
6y equals
Negative 10.
negative 10. What do I have here?
0. It's inconsistent.
It's inconsistent. What does that mean?
It's parallel.
They're parallel. They never intersect. This is how you this is how you recognize something that is inconsistent. Now, how do we recognize when they are the exact same equations? Look at example 6. All right, be thinking about how you would solve this. All right, so how would you solve this? Most of the time we do elimination. So are we eliminating x or y? x. So what do we multiply this top one by?
3,
And the bottom one?
2.
Have to multiply both of them, right? So in the top equation, we end up with 6x minus 12y is 18. And the bottom one, negative 6x plus 12y is negative 18. What happens when we add them?
Whoa.
0 equals 0. What does that tell you?
They're the same line.
They're the same line. There's infinitely many solutions to this system of equation. Yes?
How would you answer that? You would be like, infinite? Or you just
Yeah.
put it so 0 equals 0?
Infinite number of solutions. Or you could say consistent at every point. That means the same thing. Consistent at every point. Okay, so 2 by 2s are easy. Yes, ma'am. God bless you. Just a minute. Can you hold off for just a minute? All right. Example 7. How do we solve? Okay, guys. You know what? When we solve these for matrices, what did we just do to the first equation?
Oh. We just compared it to the second.
Oh, that wasn't it. I want to write the one we just did.
From example 6.
Yes. Okay. What did we do to this first equation?
You multiply.
Okay, look, I'm going to write this in a matrix. We multiplied every term by 3. Did that at all affect this second? No. Okay, so I would have ended up with what? 6, negative 12, 18. This is exactly what we're going to do when we solve them with matrices. Exactly. Then what did I do with this second equation?
Multiplied by 2.
Did that affect what I did to, I did nothing to the first one relating to that. I just multiplied this second one by 2. That's positive, huh? And then this was negative 18. Okay, this is sort of how we're going to accept. It's going to be a little different. I'll show, but I just want you to see that what we're doing with these equations is exactly what we're going to do with rows when we get to matrices. All right? So when I say we're going to multiply by one row, but it doesn't affect any of the other rows, that's what we're going to do. All right? Now let's move on to a 3 by 3. So here we have 2x plus y minus z is negative 1. We have negative x minus 3y plus z is 5. And we have x plus 4y minus 2z is negative 10. Do you remember how we solved these in Algebra 2? Yes, Corey?
You do the first 2, and then whatever you get from that, you plug into the third one. And then you get the variable.
Actually, I'm going to...
do.
What?
I thought you do the first 2 and then the second and third.
Yes, yes. We're going to do elimination with 2, then elimination with 2 others, and then we're going to have 2 equations, 2 variables. Okay, so in that, what do we want to eliminate? X, Y, or Z? Okay, we want to go to Z. Okay, so they all need to have a coefficient of 2.
So can you add the first 2 though? The 4?
Yes, you can add the first 2 and eliminate Z. When I add the first 2, what do I end up with? X, help me, X
Two
minus 2y,
equals negative 4.
4. Okay, you're with me? Okay, now we want to eliminate the same variable, so I'm going to multiply this second equation by 2. So we have negative 2x minus 6y plus 2z equals 10. All right, so what am I left with?
Negative x minus 2y equals 0.
All right, so now I have this equation and this equation.
You can eliminate x, right?
I can eliminate x. So what do I have?
Negative
Y
4,
equals
y
2.
equals 4.
So what does y equal?
Negative 1.
Negative, wait, negative. Oh,
Right? You with me? All right, now I want to go back. So I'm going to go back to this one and solve for x. So x minus 2 times negative 1 equals 4. That's positive 2.
X is 2.
So I subtract 2. X is 2. Then I go back to one of the original equations. I'm solving for z. Which one do you want to solve for?
first one.
First one.
The first one?
So 4 plus.
Okay. So, yes, 4 plus minus 1, right? Because it'd be plus negative 1. 4, I don't think we can see it on the camera. 4 minus 1 minus z is negative 1, so that's 3. So I'm going to subtract 3. I have negative z equals negative 4, but z equals positive 4. So what do we know about those equations?
They're consistent.
At just one point, right? Consistent at one point.
How do you know how many points they're consistent?
Okay.
I know how to identify if it's consistent.
I believe there's one in the next lesson that is consistent at more than 1 point. All right, let's just look at the application. We're not going to work these. Number 8. So a ball game is attended by 575 people, and total ticket sales are $2,575. What type of people attend the game?
Adults and children.
So, if I add the adults plus the children, then I get the number of people, right? And to get the ticket sales, I multiply the price times the adult plus the price times the children to get the dollar amount. Okay, that's the hard part, just coming up with the equations. Now you can use substitution or elimination. Right?
No, just elimination.
Okay, I would use elimination. Corey, I'm with you, but you could use either one. Yes. Yeah, we're going to stop here.